Hello everyone, welcome to this session. In the previous session we discussed different topologies for charge pump. We will continue our discussion on that. So, we saw three different kind of charge pump. One is source switched, where we switch the current source at its source switch charge pump. Then we saw drain switch charge pump. Okay. And after that we saw gate switch charge pump. Now, based on our requirement, we may choose between source switch or the gate switch charge pump. Drain switch charge pump comes with the by inherently it has a lot of clock feed through. Okay. So, we would like not to use that. Gate switched and source switched are the two main options which we have. But among all these three options, source switch is quite commonly used, okay, unless we are going for the differential or some other charge pump. We will see that. Okay. So, in the source switch charge pump, let us go in little bit detail. So, we have our switch like this, okay, and then we have a current source with NMOS and PMOS current source, and we bias our current source and other things in such a way that it carries the desired amount of current. So, I will just make that also here. So, this is what you have, and then a copy of this is here. Okay. So, to get the bias current, desired bias current, what we are going to do is we will pass the desired current through this, which is I naught. This generates the VBP voltage, which is passed to the NMOS, PMOS here, and this is 0. Okay. This remains 0. Then this is generated here with a diode connection, and this is VDD, and this voltage is passed like this. Okay. So, this is VBP and this is VBN. Here you use up bar and down signals, and this is what you have. Now, the current which you are going to see in these branches is, let us say, I1 and so I1 in this branch, because this is always conducting, and I will call this as I up and this one as I down. Okay. So, this is the current source which you will have if it operates. This is ICP. Now, it depends on, so ideally what we think is that I up is equal to I down is equal to I1 is equal to I naught. This is in the ideal case. Okay. And by the way, this voltage node is called as control voltage. So, this is the case. So, what happens is that you have a capacitor connecting like this, and we saw that in the previous session that you have this capacitor here. So, what happens is during the off state, these voltage nodes, we call this as Vx and Vy, these voltage nodes should ideally, as soon as this switch is turned on, this particular switch turns off, then what should happen is that the current from the upside should be equal to 0. Okay. And similarly, the current from the downside should also be equal to 0. But this V by voltage makes a transition. So, when up bar changes from 0 to VDD, during that time, this is VDD in this case, during that time your V by signal changes from close to VDD to VBP plus mod VTP. whenever your up signal up bar signal actually goes from 0 to VDD, you make a transition here from VDD to VBP plus mod VTP. So, during this process you have a current which is actually pumped to the loop filter. You have this current which whatever this node discharges from one potential to the other end. So, this current has to go somewhere, right. You can say this current sees two paths, one path is this, okay, other path is this because of the CGS capacitor. So, you have some delta ICP current going into the loop filter which creates a change in the V control voltage which is not desired. Similar thing is going to happen, that this Vx potential goes from 0 roughly 0 to VBN minus VTN, right. So, when this voltage changes from 0 to VBN minus VTN, you can think that you have to draw the current from the V control node and charge this particular node to VBN minus VTN. So, there is a discharge path which is a charging path which happens either from here or from here, and it happens from both the places, which actually changes the control voltage, or this is unwanted current which you have. So, if you do not minimize it, it will create disturbance in the control voltage, and we have seen at least at system level that if you have a change in the control voltage, this is going to modulate the frequency of the VCO, and thereby it is going to change the, it is going to add to the reference spur. So, what we can do is the following. In place of leaving this circuit as such, what we can do is, let me just redraw this. We can't remove the cap, whatever cap we are having, that cap will anyways be there, which is VBP and VBN. The thing which we can do is, we do not want to this node potential, do not want this node potential to discharge through the current source. So, what we can do here is, at this node we provide a separate discharge path, okay, and this is working with up signal. When up is equal to 0, that time this is turned off. When up is equal to 1, right, at that particular time. So, just look at it, when up, so this MOSFET is active when up signal is 1, okay, when up is 1. So, this is actually working on up bar itself. When up signal is 1, at that time your PMOS is active and NMOS is turned off. When up is 0, that time NMOS turns off and it discharges this Vx node to ground. It minimizes the current coming from the current source, this PMOS, and changing the control voltage. Similarly, on the Vy node, we can add PMOS transistor like this, it is connected to VDD, and this is working with down. So, when down is 1, at that particular time PMOS is off and you have a current path like this, okay. The current path is shown here, but when you go from down equal 1 to 0, previously your Vy node was getting okay, this is by the way Vy I have been using, this is Vx. Your Vx node was earlier going to VB minus VBN minus VTN, but now what happens is, this particular node Vx node is charged to VDD or higher potential, such that the current which is drained from the V control node, that current is minimized, okay, or reduced to 0. There are options to choose MOSFETs, both these MOSFETs with high VT or something, to make sure that this particular voltage does not go all the way to ground, it can go to some potential, okay. So, those things can be done. The basic idea is, do not allow Vx and V by nodes to charge or discharge through charge from current source while transitioning from active to inactive state. Okay. From active to inactive state. This you keep in mind. So, whatever helps you to do that, you can do that. This is one of the options. Okay. Now, well, after doing all this, we have good charge pump. So, let us see are there any problems with this, or this is good to be used in the PLL. Okay. So, now we can add the transistor which we were having here, like either NMOS going to ground, working with up bar, and this one pulled up to VDD, so that you turned off the main transistor, which is connected to down. Okay. Now, as I said that it is our assumption that I up is equal to I down, which is equal to 1 I 1 and which is same as I naught. This is the current which you control from outside. So, you have a control on this. Depending on this, your current should change at the output. Now, what happens is that if you just take these two transistors, the current sources, let us call them as MP1 and this is MP2. Okay. Based on the mismatch between these two transistors MP1 and MP2, your current I1 is going to vary from I naught. Okay. So, I will write this MP1, MP2, MP3. Similarly, this is Mn1, this is Mn2. Okay. And you will have all other transistors, I will just name it MP4, MP5, MP6, this is Mn3 and Mn4. So, now depending on mismatch between the MOSFETs, you will have the variation between I1, I naught and then I up and I down. So, you can say that I1 minus I naught, this is non-zero, is not equal to 0. Similarly, I up minus I1 is not equal to 0 and I down minus I1, this is also not equal to 0, and you have I up minus I down, this may not be equal to 0. Okay. Ideally, we know that all these current sources, they have to be same, but these current sources are not same all the time. Okay. Now, if these current sources are not same all the time, what are the effects? That is one thing which we need to understand. The other thing which we need to know is that is there some way that we can fix that. Okay. Other thing is that this is only depending on the mismatch between the MOSFETs which you will have, and this particular mismatch is called as static mismatch. Okay. Why it is a static mismatch? Because when you design this circuit, whatever mismatch you have, that mismatch will remain, that mismatch will always be there. It will not change during the operation of the charge pump. Okay. So, this is one mismatch which you will see. Other mismatch which you are going to see is V control. So, the current which you are going to see coming from I up or I down, that also depends on V control. Okay. So, you can say you have channel length modulation for the current sources, whichever current sources you see, right. Based on the channel length modulation, the current you will again have the mismatch. So, I will write that channel length modulation introduces mismatch between the current sources, okay. And why it will be there in during the regular operation? The V control node which you are having, right, this V control voltage is decided by the PLL feedback loop, which is this is the control voltage of the oscillator. So, V control can vary. If V control varies, then you see that the VST of the PMOS and NMOS here, right. This is different from the VDS of the PMOS here, VST of the PMOS here and VDS of NMOS here. So, if your drain to source potential for NMOS or source to drain potential for your PMOS differ, then they cannot have the same current. Okay. So, this is another mismatch which you will see between these current sources. The other one is that when you are making a transition, right, when your up pulse, if you look at it, this I up and I down. Okay. So, when my up signal makes a bar signal makes a transition from 1 to 0 like this or high to low like this, your I up current, this particular current will go from 0 to 1, okay, in some time. And when you make it when you make your up bar signal to go from low to high, then your I up current will go from high to 0, something like this. Okay. So, even when this current, which is the current when you say okay, when it has reached steady state, this current may be same for both up and down pulses. Okay. So, you can look at I down and I down current depending on your down signal. I down current may be like this, okay. So, you may have this current same as this current, but during the transition, right, which you see this current is not the same as the current here. And these things will happen because in this case you see that the PMOS, one transition is happening, I up current is coming because of the PMOS, which will not respond with exactly in the same manner as your NMOS is going to respond. So, these two PMOS, they will respond differently as compared to NMOS. So, you will see the difference in the current. In a steady state, well, when it settles, then during the settling process the current is same. Why it does not respond in the same way? Because PMOS mobility is different, the parasitic capacitors are different, how much time it will take for this node up bar node to go from 1 to 0, and then how much time it is going to take V by to go from some 0 voltage to VDD and then get the this current source activated, right. These timings are going to be different from your timings for the NMOS. So, there is going to be a mismatch here. Okay. That is another mismatch which you will see in these current sources. Another one, so this is a kind of you can say a dynamic mismatch in the current sources. So, you have dynamic mismatch, and one dynamic mismatch is because of transition time difference for PMOS and NMOS. Okay. That is one thing. Another thing is that when your control voltage is changing. So, one thing is that in a steady state, if the control voltage remains fixed, then you do not have any then the current source will always remain fixed. But every reference clock or depending on the feedback required, control voltage may have a ripple. or let us say this ripple is not because of the charge pump, the ripple is because of the other things in the PLL, right. Also the control voltage may need to vary across the across the frequency range which you need for your PLL. So, if your oscillator goes from x frequency to 2x frequency, control voltage may vary by 2x. Okay. So, if control voltage changes, in that case also your output current will change. Okay. So, because of the change in the control voltage, this control voltage is the control voltage of the oscillator. Change in the control voltage during the regular PLL operation, you will have the difference between I up and I down. Okay. So, there are multiple reasons for which you may see a mismatch between the up and down current sources from the current source, from your external current source which you are using for biasing the charge pump, and this mismatch creates additional voltage ripples on the control voltage, which in turn creates the reference spur. So, let us just understand that how these kind of ripples are going to create and what is going to happen in the PLL. Okay. Once we know that what problems it causes, we will try later to address and minimize this mismatch. Okay. Now, to begin with, let us take the case 1, okay, where you for any particular reason you have a mismatch between up and down currents. Okay. So, two cases we will study here, that when you have up and down mismatch current. So, I up is not equal to I down, whether it is coming from your MOSFET mismatches or it is coming because of the channel length modulation, this mismatch exists. So, when this mismatch exists, what will happen is, by the way, you are having your PFT which gives you signal up bar and down to control the charge pump. This is what you will have. You have these signals R and V. V is the feedback signal, R is the reference signal. So, ideally in a steady state you should have R and V aligned, but now if I do that, let us say R and V signals are aligned like this in a type 2 order 3 PLL. If this happens, then we know that our up bar and up and down signals, they will have a certain overlap period in this manner. Okay, this will happen when you have the phases aligned, right. You will have up and down, but because your I up minus I down is non-zero, right. So, your charge pump current will be, you will see a current ICP with whatever difference you have, I up minus I down current like this. Okay. So, if someone has forgotten the PLL block, I will just draw that. Okay. So, we are having PFT followed by charge pump. Okay. We are using source switch charge pump, then we have loop filter RC1 and the other one is C2, right, and then you have VCO with a divider in the feedback, and this comes back here. Okay, this is R and this is V, by the way. Here this is your output of the PLL. So, we are talking about this ICP and this control voltage, right. So, this will happen if there is a difference between I up and I down, and that difference I am calling as delta I. Okay. If you are going to add this current to the PLL, then the control, because you are adding this ICP waveform here has non-zero DC value, which means you are adding a DC current to the capacitor. So, voltage will always keep on increasing, and if this happens then you are going to saturate. But because you are operating the PLL in a feedback loop, this does not happen. So, what happens is that the PLL itself will actually create an offset in such a way that the average current which goes into the capacitor, that is 0. So, how does it do that? So, this is what you see, that I up is greater than I down. So, during the overlap period this will happen. So, what I need to do is, in order to compensate for this current, I have to add a negative current, which means that I have to create a negative phase offset. So, the PLL itself is going to do the following. It will create an offset like this in feedback, because that is what the PLL will control. Now, when you have an offset like this, so your down signal will go high here, but up signal goes high like this. Okay. This will happen, your up signal goes like this, and the overlap period is now. So, you have a negative phase error, and this is your overlap period, and this is going to repeat. So, with respect to our original case, what will happen is, during this time when you have a negative phase offset, you will have a negative current which is I down, right. When you have down signal as active, you will have I down current, and then for the overlap period you will have this value. Okay. So, this T offset is created by the PLL loop, and it is done such a way that this current which you are seeing as I down, and this is the delta I current, such that these two things are going to give an average current to the PLL, average current to the loop filter, which is 0. So, that in a steady state you do not have any change in the frequency. Okay. So, now with respect to this current, if you think about it, ICP R I have. So, I will just now magnify this, let us say here. In the presence of the mismatch between your currents, right, I am going to have a current like this from 0 ICP to I down value, and then the overlap period like this, okay, and this is the thing which is going to repeat every reference clock period. Okay. It is going to repeat. This value is I down. So, if I write it, let us say your I up is greater than I down. So, I up is equal to I down plus delta I. This is what I have. So, here this value is I down, this value is delta I. This offset is T offset, this region, and this is T overlap. Okay. So, in a steady state, what you are going to see is that your I down times T offset, that is the negative charge, right, is equal to your delta I times T overlap. So, T offset value which you are going to have is delta I by I down times T overlap. So, I down I am just writing as now I CP, okay, times T overlap, right. So, this is what you are going to see, right. It will create an offset value which is given in this manner. Now, in response to this steady state disturbance in the current source, okay, you are going to have a change in the control voltage. And how will the control voltage react now? So, if you had only this loop filter, a part of the loop filter I am drawing R and C, because going with the both of them becomes little difficult to visualize. So, if this is my loop filter and I have ICP the way I have shown you like this, I will again draw here with maybe an enlarged value. This is ICP, and then I have a large portion which is T overlap. Now, this is repeating. So, this is your total time period T. Okay. This is my T offset. So, in response to this ICP, I am going to have V control voltage. ICP is negative. So, your V control voltage will take a jump, okay, and then it will integrate in the negative direction, okay, right. This is I down R jump you are going to have, right, and then it will be a reverse jump like this, right, and then what you are going to have is with respect to this. So, there is going to be this jump, and then you are going to integrate in the opposite direction, and then again you are going to, this is what you may have in general. Okay. If you only look at, this is what will happen if you have this loop filter. So, if you want to look at it, you look at in two parts. One, the V control which you are going to have is only ICPR jumps which you see. So, one is like this, okay. ICP is minus I down R, and then you have ICP times this is the jump, and then, so I can write this is as simple ICP times R, and this value is delta I times R. So, this is the control voltage jump. Other part which you are seeing is nothing but the integrator part of it. So, that integrator part of it, what it is doing? It is doing something like this. Ideally, okay. So, the absolutely if you look at it, V control which you have here, this V control is sum of these two. So, the total charge, what I am saying is you start with V control as 0, you go negative, but at the end you again you have V control as 0. Without this offset, what you may have here is only with the blue one, you may have V control going always in one direction and remaining there, okay. But now what you see is that V control decreases, and then it gets back to 0. So, in the presence of the second capacitor, things change a little bit. You do not have a sharp jump here, you have a slower jump, but still you will see that effect. Okay. So, let us look at first only with the simple loop filter R and C1. Okay. So, now this particular jump which you are seeing, this ICP R, normally you will have ICP times R much larger than, okay, delta I times R. And why I am writing like this? Because I am going to decompose this particular part as two of the pulses, one which is this, which is a large pulse like this every clock period, and the other one I am going to write it like this, okay, in this manner. Okay. So, this is only let us call this as V control P and this as V control I. So, I am decomposing V control P as some of these two waveforms. What happens is that the one of the waveforms which you see is having a much larger magnitude as compared to the other one. So, this creates a more reference, this creates a larger reference spur as compared to this part. Okay. So, we can analyze the one which is dominant, and the one which is dominant is ICP times R. So, let me just redraw V control voltage, V control P for example, and what you have here is like this. This is repeated at every frequency in this manner. Okay. This is your time period T, and for how much time? This is for T offset jump ICP times R. Okay. You can have a negative jump, you can have a positive jump. So, I can very well say if your I up is lesser than I down, then you may see such kind of jump. Okay. So, there is nothing like you can have only one kind of jump, you can have both positive or negative. Okay. So, now this is a periodic disturbance in the control voltage. For this periodic disturbance in the control voltage, you need to find out that how it is going to change the frequency, or it is going to cause any disturbance at the output. So, the standard procedure is that you write this V control P of T as a Fourier series. Okay. So, I will write A naught plus summation of A n cosine of n omega naught. Here it is happening at reference frequency. So, I will write n omega r t plus B n times sine of n omega r t. Okay. So, you will see that you are going to get a lot of component magnitude here. So, if I go and find the Fourier series component for this, right, I will get the fundamental. So, omega r here is the reference frequency. Okay. And I am just writing it for the positive one to not to get confused with the negative sign during our calculation. So, this let us say this is ICP times R also here. Okay. So, when I go ahead and do this, what I will find is that you have here both the sine and cosine components. You can compute the values for both, and to compute the values it is an easy way. What you are going to do is V control P of T, integrate this. If I want cosine, I am going to multiply with cosine of m omega r t, integrate over one period. This is going to give me the coefficient for am cosine of m omega r t, all other coefficients will be 0, cosine is square times dt. Okay. You are going to integrate over one period such that your omega r is equal to nothing but 2 pi by t. So, to calculate this, we know that the V control of P is actually non-zero only during the time 0 to t offset. So, I will have this ICPR going from 0 to t offset. Cosine of m omega r t will remain inside the integration. You have m omega r t dt, and for the other one you see that it is cosine or square of m omega r t. So, I can write it as 0 to t into 1 plus cosine of 2 m omega r t dt. This integration over the time period is going to give us 0. So, what we are going to get here is a m by 2 times t, and this integration ICPR cosine integration is sine, okay, m omega r t whole divided by m omega r, limits are 0 to t offset. Okay. So, this is going to give us that your a m is equal to 2 by t times ICPR, okay, sine of m omega r t is sine of m omega r t offset. Okay. So, this is what we get. To find b of m, right, I will just do the integration with respect to sine. So, 0 to t b control of p times sine of m omega r t dt. This integral 0 to t times bm of sine square m omega r t. Okay. Now, this again the same logic, ICP times r comes out, 0 to t offset sine of m omega r t times dt. This is equal to bm by 2 0 to t into 1 minus cosine of 2 m omega r t times dt, right. So, this is ICPR sine omega m omega r t integration is minus cosine m omega r t divided by m omega r 0 to t offset. This is bm by 2 times t. So, I can write bm as 2 by t whole divided by ICP times r into cosine, this is m omega r, and 1 minus cosine of m omega r t offset. Okay. So, you see these two components, the thing is that your t offset is quite small, and when t offset is going to be quite small, this cosine of the small value is like equal to cosine of 0, which is equal to 1. So, bm component will be more or less equal to 0. So, we will focus on this component only. Okay. So, when we focus on this particular component, okay, and the DC component, we know here that the DC component is going to be cancelled by the other offset component, right. So, in this case we can write we control P voltage as A m, which is 2 by T ICP R divided by so this is m omega r we missed here, m times omega r, okay, m times omega r times sine of m omega r t offset. You have cosine of m omega r t. Okay. So, when we have this as a control voltage where we focus right now only on the fundamental amplitude. So, when that is the case, we know your V out of the oscillator is nothing but some magnitude times amplitude times sine of omega free plus k VCO times V control dt, right. This is what we have, which I will just write it as A times sine, let us say whatever your omega naught frequency is, omega naught t, plus what we are getting from here is the variation. I will write that variation as cosine of m omega r t. So, you see k VCO times beta into cosine of m omega r t dt, right. This changes to sine of omega naught t plus k VCO times beta, right. This is what you have, and cosine m omega r t, this integration is going to give you sine of m omega r t divided by m omega r, right. So, you get this particular voltage at the output, right. Now, if you look at it, you have a sine of omega naught t plus k VCO times beta, which is beta is nothing but I will write this beta as a whole. Okay. So, you write 2 ICP r divided by m omega r times sine of m omega r t times sine of m omega r T s. T offset times sine of m omega r t. This is the expression which you have, okay, absolute expression, but we are going to do a simplification here, where V out of t, this comes back here, is a sine of omega naught t times cosine of k VCO beta by m omega r times sine of m omega r t. Okay, a sin theta plus cos theta, sin theta cos theta plus cosine of omega naught t times sine of k VCO beta by m omega r times sine of m omega r t. Okay. So, now we will make an assumption that this value or whatever the argument of this is quite small. We know beta is normally quite small, and then you have another factor of m omega r in the denominator. So, beta is this whole, call this as theta. If theta is quite small, then cos theta is 1 and sin theta is theta. So, I will substitute that. You have sin omega naught t plus a times cosine of omega naught t times k VCO beta by m omega r times sine of m omega r t. This can be written as sine of omega naught t plus a by 2 k VCO times beta by m omega r 2 sin a cos p. Okay. So, if it is 2 sin a cos p, you can write it as sine of omega naught t omega naught plus m omega r times t, right, minus sine of omega naught minus m omega r t. This is what you are going to see in the output spectrum. Okay. If m is equal to 1, then I can write that m is actually equal to 1, okay. And with respect to m equal to 1, let us just simplify this. So, further you are going to see references, you are going to see spurs at reference and its harmonics all the places. So, V out of t has the frequency omega naught, plus it also sees the magnitude k VCO beta by 2 m omega r at omega naught plus omega r and omega naught minus omega r. So, I will just plot this, that is a better. So, a spectrum of V out, whatever value it has here, if this value happens to be 1, then you will see it is flanked by values at omega r, and so this is omega naught, right. You will see omega naught plus omega r, omega naught minus omega, sorry, plus 2 omega r, okay, and this is omega naught minus omega r, this is omega naught minus 2 omega r, and this amplitude is going to be at the your mth harmonic. So, amplitude at omega naught plus m omega r is k VCO times beta divided by 2 m omega r, which is equal to k VCO by m 2 times m omega r. Beta is something which we have used before, which is ICPR times m omega r into sine of m omega r t offset. So, depending on your t offset value, you are going to see the whisper. Okay. So, this is how we can, I have worked out for one particular case when you have a current mismatch because of up and down. You can do the same thing for any mismatch, whether it is up and down mismatch or it is a direct mismatch because of the control voltage. The same logic will apply and you can always work this out. Okay. Thank you.